We've seen in the last set of videos how the psi of t times the psi inverse of S matrix gives us what we call the propagator matrix phi of ts. Now, the thing I just want to remind you of right now, because we're going to go on and talk about the exponential of a matrix, powers of a matrix, and so forth. But the thing I want to remind you of, or really point out, is that when you do this, and you should have done this by now, but you can verify this, and if you don't get this, then there's something wrong, okay? But if you do a psi of t times psi inverse of s, this is just a function of t minus s. Okay? So this could be written as phi of t minus s, if you wish, a single variable t minus s. But since there's an s and a t, we write it as phi of ts. Okay. And if you replace t by t minus s on a graph, what do? You shift that graph s units in the t direction, which is generally considered to the right. So that would be a horizontal shift of s units. A shift of s units to the right. Your whole graph would shift s units to the right. So the point is then that phi of ts shifts a phi of t0 graph s units in the t direction. That's important, and that's important for the idea of a propagator matrix, which has the property that it propagates a solution from one point to another. Since this thing translates from one point to another, it's plausible that we could use that in some way as a propagator. We'll see more about what that means and tie it together with this whole exponential of a matrix and so forth. And we'll see why we want to talk about the exponential of a matrix before we do that. Now, as I said before class today, you should review the Taylor series for the exponential function and the sine function and the cosine function, and in general, how you get a Taylor series. It's very straightforward if you can just see the pattern to the derivatives of a function. And I'm not going to go over it, I'm not going to explain it, maybe at some point, but e to the t, though, the Taylor series for e to the t is just 1 plus t squared over 2 factorial plus t cubed over 3 factorial, and that keeps going forever, and the typical remember the sequence, or the typical nth term, term's the word I was looking for, the typical term of this series is t to the n over n factorial. Now, it's not too hard to understand sine of t. Okay, in the first place, if you just take successive derivatives of the sine, you see that the sine of t can be written t minus t cubed over 3 factorial plus t to the 5th over 5 factorial. That kind of looks like a 5 prime, but that's the dot under the factorial sign there. T to the 5th over 5 factorial. And the general term can be written negative 1 to the n. Okay, that way, here's your n, well, your n equals I'm not sure I like the way I wrote that. It works. Okay, your n equals 1 term, if you wish. If n equals 1, you get negative 1 to the 1, and t to the 2n plus 1 would be 3. I'm sorry. No, I'm sorry. The n equals 0 term. Okay, and that's probably not the best way to write it now that I look at it. And maybe I'll correct that a little bit and explain why. But if n equals 0, you get negative 1 to the 0, which is 1, multiplied by t to the 2n plus 1. Well, 2n is 0, so that's t to the 1. And 2n plus 1 factorial, that's just 1 factorial. So you're just getting t over 1, and that's t. Okay? Your n equals 1 element would be a negative 1 to the 1, which is negative 1, giving you a negative sign. T to the 2 times 1 plus 1, that would be t cubed. and that would be 2n plus 1 factorial. If n is 1, that's 3 factorial, and that's your negative t cubed over 3 factorial, and so on. Now, I think there's a better way to have written that, but yeah, that works, and we at least get the idea of how this comes about. And the cosine of t is this, and you can verify, first of all, if these are the first 3 terms, if you just do the derivatives, and you can verify that for n equals, and I didn't write that down right, I got negative 1 to the n, so if n was equal to, never mind, that's right, okay, negative 1 to the 0 is 1, t to the 0 is 1, 2n is 0, and 0 factorial is 1, you get 1. I don't know what I'm thinking. Okay, so n equals 2, you get a negative from this, you get t squared over 2 factorial, you get this. If n is 2, you get a positive again, negative 1 to the 2nd power is 1, that's t to the 4th, and that's 4 factorial, and so forth. Okay, I thought I'd written those down right, I don't know what I'm looking at right now. Okay, now, if A is a constant matrix, then I'm claiming we can write e to the ta equals, well, just what you would get if you plug ta in instead of t here. If e to the t is this, then e to the ta is going to be 1 plus ta plus quantity ta squared plus over 2 factorial plus quantity ta cubed over 3 factorial, and so forth. Okay, and that's just what I've written down here. The general term would be ta to the n over n factorial. Now, does it make any sense at all to do this? Like, for example, is the derivative of e to the ta equal to a times e to the ta, as it should be if the chain rule is going to hold? If it is, then you start beginning to believe there's some validity to this. Well, it turns out there is, and we'll see why. And also, you can see that if A is just any old matrix, I just write down some matrix, and want to find its general nth power, that's going to be really hard to do, isn't it? Okay, you're going to have to multiply the matrix by itself n times. Yeah, you shortcut that. You can multiply it by itself and get its square. Multiply that by itself, you get its 4th power. Multiply that by itself, you get its 8th power, and so forth. You get exponents that are powers of 2, and then you can use products of those to get any exponent you want with less work. And you don't understand what I just said, but it's true. There are ways to shortcut it, but it's still a tremendously computation-intensive process, and you never really can prove you've got much of anything if you do that. But however, in fond memory of one of my graduate school professors, but however, products of diagonal matrices are easy. Okay? We can see that very easily. Just take a 2 by 2 matrix and go ahead and put lambda 1 and lambda 2 on the diagonal, because usually if you diagonalize the matrix, you diagonalize it with eigenvectors, eigenvalues. What do we get if we square that? Okay, well, I asked everybody write down ta squared, ta cubed, ta to the n. Okay? Well, and then I plus ta quantity squared over 2 factorial plus ta quantity cubed over 3 factorial. Okay? And people pretty much didn't have too much trouble doing that. Not sure what this smudge here indicates, but I don't think it means anything, so let's get rid of it, because it's probably, oh, I get it. That wasn't a smudge, that was a exaggerated subscript 1. Okay, so probably looks worse than it did before, but there it is. Okay, well, TA, if A is this, TA is just what you get when you multiply every element of the matrix by T. And if you multiply 0 by T, you get 0. If you multiply lambda 1 or lambda 2 by T, you get lambda 1 T or lambda 2 T. That's easy. Okay, then TA squared. Okay, well, I claim that's equal to just this squared and this squared with the zeros here. And you can see that easily enough. Down here, I squared the matrix lambda 1 with lambda 1 and lambda 2 in the main diagonal, zeros off the diagonal. Lambda 1, 0 times the column lambda 1, 0 gives me lambda 1 squared, clearly. The row lambda 1, 0 times the column 0 lambda 1, well, that's lambda 1 times 0, which is 0. And 0 times lambda 2, which is 0, that adds up to 0. And you can similarly verify if you multiply the second row by the first column, you get a 0 in every term, so you get this. And the second row times the second column, you get 0, but you get lambda 2 squared. You can continue this, but if you do, if you do, okay, let's say you did lambda 1, lambda 2 times lambda 1 to the n, lambda 2 to the n. What would you get? You get lambda 1 to the n plus 1 by multiplying the first row by the first column. So that would be lambda 1 to the n plus 1. You get zeros multiplying the first row by the second column and the second row by the first column for the same reason you did before. But when you multiply the second row by the second column, you're going to get lambda 2 to the n plus 1. It's kind of smudged, you might not be able to read it. Well, this proves that if you multiply the diagonal matrix by the matrix with nth powers of those diagonals, you get the matrix with n plus 1 powers in those diagonals. Now we just proved if you multiply the matrix by itself, you get the matrix with squares in its diagonals. So if n is equal to 2, you multiply it by the matrix and you get 3's here, right? So it's true for n equals 2, giving you, well, it's true for the cube of the matrix. And if it's true for the cube, then it's true, then the cube would be lambda 1 cubed and lambda 2 cubed, and you multiply that by the lambda 1, lambda 2 diagonal matrix, you're going to get lambda 1 to the 3 plus 1, lambda 2 to the 3 plus 1, lambda 1 and lambda 2 to the 4th. So if it's true for the 4th power, well, you put the 4th power in here and you find it's true for the 5th power. If it's true for the 5th power, you put it in here and you find it's true for the 6th power. So you've proven that it's true for the square, for n equals 2. And you've proven that if it's true for n, it's true for n plus 1. So you don't even have to go into this. You can just say, okay, well, it's true for the square, so it's got to be true for the cube, so it's got to be true for the 4th power, because it's always true for the next power. Okay, well, with that fact in our arsenal, it's really easy then to write down these powers. TA, quantity squared, is just, well, you square this, and you get zeros there. And then we can do TA cubed and TA to the 4th and so forth. Also, we note that TA to the 0 could be defined as the identity, and it would be consistent with this process, so that's what we're going to do. So this is just TA to the 0. Well, okay, those are powers of diagonal matrix, and you see that it's really easy. And also, this isn't just confined to what would happen if you had a 2 by 2 diagonal matrix. If you had an n by n for any n, the same thing would happen, and the same argument could be made. So we see that we can do these powers of TA, which starts to make more sense out of the idea of an exponential matrix. So we'll see where that goes in a minute.